A'udzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum warahmatullah. Let's continue our discussion on the metal forming process. In the last lecture, in lecture number 10 and 11, we discuss fundamentals of metal forming, in which we discuss how the flow stress works and the difference between the engineering stress and the true stress, and the effect of a strain rate on the material during the hot working. So in this chapter we are going to discuss each type of bulk deformation process separately. So let's start with our first type of bulk deformation process, that is rolling operation. So again, where we are standing right now, we are basically discussing the bulk deformation. Among the deformation process, we are discussing bulk deformation process, and in the bulk deformation process we are going to discuss rolling operation. Right, we have forging, extrusion, and wire and the bar drawing. So we'll briefly discuss the background of the rolling operation. Rolling operation, as the name suggests, is a deformation process. It's a bulk deformation process, and what was the identification of the bulk deformation process was, it's a type of metal forming process in which we achieve the significant shape change. Our purpose is the attainment of the significant shape change, and that shape change is achieved by applying the stresses or producing the plastic deformation. So that's why it is a type of deformation process. So it is used in the parts whose initial form is bulk rather than the sheet. And if you remember, what was a bulk? Which has the lower surface area to volume ratio, while the sheet has the greater surface area to volume ratio. So the common starting materials in the rolling operation, the cylindrical bars, billets, and some rectangular billets, slabs, and similar shapes. We will see what the billets and the blooms and what they are actually. So how does it work? These processes work by stressing metal sufficiently to cause plastic flow into the desired shape. So, and they are performed as a cold, warm, and the hot working. So these are some the same things which we have discussed in the last chapter. What is the purpose of this? It produces shapes inexpensively or without much cost. It's cheap process to produce shape change. The final product has a good mechanical properties, and the last thing is important one, it has a little or no waste. So what is the rolling operation? Rolling operation is a deformation process in which work thickness is reduced by compressive forces exerted by two opposing rolls, like this one. So the two opposing rolls are not only, by the rotation, they are not only pulling the workpiece into this gap. Once the workpiece enter into this gap, they apply the compressive forces to reduce the thickness of the slab. Right. So in the last lecture, while we were discussing the introduction of the rolling, I said that these rolls are pushing the workpiece. So I would like to rectify that. It was actually these rolls are pulling the workpiece into this gap and applying the compressive forces to reduce the cross section or the thickness. So what is the starting workpiece? The work starts out as a steel ingot or the cast iron steel ingot that is just solidified. We use casting operation to form ingot, and as you know, in casting operation, material is in the molten form, so it solidifies to form the ingot. So while the material is still hot, due to the casting just solidified, while it is still hot, this whole ingot is placed into the furnace. This whole hot ingot is placed in the furnace. So what is the purpose of putting this in the furnace? So that once it is placed inside the furnace for a long period of time, so it will have a uniform temperature throughout. So the plastic deformation that is produced will be uniform in all the regions of this workpiece. So for this purpose, let's suppose a steel ingot The desired temperature for rolling is around 1200 degrees centigrade. So it will be placed inside the furnace, and this process of placing the ingot into the furnace for the sake of homogenizing the temperature or to attain the uniform temperature throughout, that process is known as the soaking, and the furnace that are used for this purpose are termed the soaking pits. So what are the common shapes that we can achieve from the rolling operations or different types of the rolling process? We are starting with the ingots. That ingots are deformed into the blooms or the billets or the slabs. So the starting workpiece will be this one. By using the simple rolling operation, we can transform them into the blooms and billets or the slabs. So these blooms and billets can be further used to form either bars or which have a further lesser cross-sectional area, or they can be shape rolled. There's a special kind of rolling that is will be performed on it. On these billets and blooms, they will be shape rolled to form certain shapes, or the slabs can be further compressed to form the plates or the sheets and strips. So these are some common shapes that can be achieved by different kind of rolling operations, and we will see this in the slides ahead in this lecture. So the rolling operation can be divided based on two things. The first one, the geometry of the work, and the second one, the temperature of the work. As the temperature of the work we have discussed in the last lecture, so we can have the hot rolling operation, that is a hot working, or we can have the cold rolling operation. If we are performing the hot rolling, so our main purpose is to produce large amount of deformation. Our main purpose of the hot rolling would be to cause significant plastic deformation or shape change, while if you are performing the cold rolling, our purpose would be to produce high strength sheets or to increase the strength of the material, the workpiece. While the other basis of the classification is the geometry of the work, what kind of product we are obtaining. So based on that, rolling can be of two types, either the flat rolling or we can have the shape rolling. Flat rolling, which is just reduced to thickness, used to reduce the thickness of a rectangular cross section. We have just a slab, so the flat rolls are applying pressure over it to flat rolls will be applying pressure over it right. So only purpose would be to reduce the thickness of the slab. While in the case of the shape rolling, we can have the shapes on the rolls, on the rolls that are performing the rolling operation to attain the desired shape in our final part. So we can form the I-beams on different kinds of beams using the shape rolling operation, and you will see how does it occur in the types of mills that are used to perform the shape rolling operation. So how does it work? As we have discussed, it works in two steps. The first step is that the rolls that are performing the rolling operation, it pulls in the work material. They pulls in the work material by the effect of friction, and once the work material enters into this gap, they apply the compressive forces and reduces the thickness of the material. So let's suppose we have this roll. We have this roll, and that has a radius of r, and a slab is being compressed between the rolls such that the width of the slab, initial width of the slab is w0, and the initial thickness is h0 or t0, whatever you would like to write. Initially it has some velocity of v0, and it has some velocity after passing through the roll, that is vf. Then there's a contact length. As you can observe here, there's a contact length of between the roll and the workpiece. There's a contact length here between the roll and the workpiece, right? So this is the contact length, that is L, and we have some final thickness WF and the final width WF and the final thickness TF or HF. Then we can see here there will be an angle of contact between the roll and the workpiece. There is a roll gap, that is what is a roll gap? The distance from the entry zone to the exit zone, right? A distance between the entry zone to the exit zone, that is the roll gap. We have frictional forces that are exerting during this contact length, along this whole contact length, right? And there will be some torque on the rolls obviously, and they will be using some power as well. So this is how it works. We have some initial width dimension of the workpiece, we have some final dimension of the workpiece. There's a contact length which we need to determine. What is the contact length between the work and the roll, workpiece and the roll? There is some angle at which the roll is entering into the this gap at which the workpiece is entering into the gap between the rolls, and there is a roll gap, that is a distance between the entry zone and the exit zone, and here the frictional forces are actually working to pull the workpiece into the gap. So let's start with the analysis of the rolling. So we have the first one, the draft. While performing the rolling operation, the first thing we consider is the draft, especially the flat rolling. So what is the draft? Draft is the amount of thickness reduction. Draft is the amount of thickness reduction, and that is equals to initial thickness minus final thickness, right? So that is the initial thickness, and this one is the final thickness. Then the second terminology, that is a reduction ratio. And that is represented by R, and it is equals to draft divided by the initial thickness. Or we can simply write as T naught minus TF so this is the reduction ratio. So it is simply a draft expressed as a fraction of the starting stock thickness. So when the series of rolling operations are performed, reduction is taken as a sum of drafts divided by the total thickness. So there is a type of the rolling operation in which the thickness is reduced gradually. So how does it occur? We have series of rolling operation that is taking place. So how do we calculate the reduction? It is taken as a sum of draft here, here and here, and divided by the total thickness. Okay, this is how we calculate the reduction ratio when there is a series of rolling operation. So while performing the rolling operation, obviously our dimensions are changing, but the volume is constant. So by the constancy of volume, we can write it as T naught into the initial width into the initial length equals to final thickness into the final width into the final length, right? And there is a thing, when we say that the thickness of this is being reduced, so obviously it is being some other dimension is also being changed, because if the thickness is reducing in this direction, if the thickness is being reduced, it means some other dimension is being increased, because the volume is constant. So it do occurs in the case of the rolling, and some empirical observation is that after each roll pass, the strip thickness reduces whereas the width increases. You can say the strip thickness or the slab thickness. Whereas the width increases, and that is approximately, width increases by approximately 2%. So WF equals to 1.02 of W naught. So WF is equals to 1.02 of W naught. So this increase in the width of the material, the workpiece, during the rolling operation, that is known as the spreading. It is called as the spreading. Right? Material is spreading along the way. So there's a spreading during the rolling operation. There's a reduction in thickness, but at the same time the width of the material increases. So there's empirical observation how much it increase in a single pass. So after each roll pass, so it is about each pass, when we are performing the rolling operation, so it occurs that we pass the material one time, then we again pass it another time, then we so on and so forth. So we pass the workpiece between the rolls multiple times. So in each pass, there's empirical observation that the width of the workpiece increases by 2%. So the final width after each pass would be 2% greater than the initial width. So this is known as the spreading. So once we have the constant volume, so the volumetric rate would be constant before and passing the roll and after passing the roll. So we can simply divide it by the time. So we can write it as T naught W naught into V naught initial velocity into TF WF into VF, right? Because we have divided by time to get the volumetric rate, and that length by time, it becomes a velocity. So we have initial velocity and the final velocity of the material of the workpiece. In the last slide, as we have seen, if we see here in this region, the roll contact the work along an arc, right? The roll contacts the work along an arc defined by the angle, this angle alpha, right? So each roll has a radius, as we have seen. Each roll has its own radius, and its rotational speed gives the surface velocity of VR. So this is VR is the velocity of the roll, which we have find out using the rotational speed of the roll, and this velocity is obviously greater than the velocity of the workpiece before entering into the gap, right? And but it is less than the velocity of the workpiece after passing through the gap. And as we know that the metal flow is continuous, there's a continuous flow of metal between the rolls, so this change in velocity of the workpiece before and after, it gradually occurs, right? So it gradually, like it was lower before, and it is higher than the roll speed after passing through it. So obviously, let's suppose if we have the VR like this, at this point we have VR, and this is our V naught, and our V naught is increasing, and at some point it will be equal to VR, and after passing through the roll it will be greater than the VR. So our VF would be greater than the VR, right? So obviously there will be a point in this contact length, in this the region of contact. There will be a point at which the V naught, the velocity or the velocity of the workpiece, would be equal to the velocity of the roll. So that point, that one point, is termed as a no slip point, right? So that point along this contact length, so let's suppose our workpiece has entered into the roll gap. Now the velocity of the workpiece is increasing, its force is also increasing, so there will be a point at which the workpiece will have the same velocity as the uh, roll that is performing the rolling operation. So our V would be equals to VR, and that point is termed as a no slip point, or also known as a neutral point. On either side of this point, slipping and friction occurs. So why it is called as a no slip point? Because it has the maximum friction, it has a maximum friction here, so such that and so that the velocity have become equal, they are moving at a same speed. So there is no slipping occur, because once if you observe the rolling operation, when the slab passes between the roll, and as we know the roll speed is greater than V, is greater than the velocity of the workpiece. So obviously there will be some slipping occurring here, and there is not a perfectly interlock contact, so there will be some friction slipping occur. But at a single point there is no slipping, and that is termed as no slip point, and at that point VR becomes equals to V, right? So the amount of slip that occurs between the roll and the workpiece, so we can write it as the amount of slip that occurs between the roll and the workpiece as Vf minus VR, the velocity of the roll, divided by the VR, right? Where S is termed as the forward slip, and we have Vf is the, you can say, exit velocity of work part, and VR is the roll speed, right? So this is what the neutral point is. Neutral point, the point where there is no slipping occur. And why there is no slipping occur? Because the velocity of the roll becomes exactly equal to the velocity of the workpiece at that point. Now moving towards analysis of the rolling operation. So what kind of strain that would be acting on the workpiece, or what would be useful for us actually, as we have discussed in the last chapter, that in the deformation process or the metal forming process, we primarily concentrate on the true strain, because that is what is used to calculate the flow stress. And what was the flow stress? The stress that is required to continue the deformation. So in the rolling operation, there is a requirement to continue the deformation while performing the rolling operation. So the true strain in this, let's suppose this is our rolling operation, so the true strain we can write it as strain equals to ln of T naught by Tf, right? And as we can see here, the pressure is being applied gradually. There is no impact load by the rolls. The rolls are not applying impact loading on the workpiece, rather the pressure is being applied gradually. So what kind of flow stress we'll be considering for the rolling operation? That would be the average flow stress, right? So what was the average flow stress? That was equals to strength coefficient into the strain hardening into the strain into exponent strain hardening, divided by 1 plus n. So the average flow stress is used to calculate the force and power of rolling. However, there's a limit to the maximum possible draft, right? What was a draft? Draft was a difference between the initial thickness and the final thickness. So it is not the case that you keep on applying the pressure and it will give you the draft value. The draft value will keep on increasing. There's a limit to the maximum possible draft that can be produced by the given roll, right? So how do we calculate the maximum possible draft? That is equals to so the maximum possible draft is termed as d max equals to m square r. This is the maximum possible draft that can be produced in a single pass. So it's a maximum possible draft that can be produced in the single pass. So what were the drafts? Difference between the initial and the final thickness, right? So here we can write it as, here m is a friction coefficient, while the r is the roll radius, as you can see here, right? So the coefficient of friction in this case of rolling depends upon the lubrication that we are using here, and the work material, what kind of material that is being used, and the working temperature. Obviously if it's a hot working, there will be more friction, right? So in the case of the cold working, the value of m in the case of the cold working, the value of m is equals to 0.1. in the case of hot working, this friction increases, so we have a friction coefficient of 0.4. in the case of the warm working, we take the friction values equals to 0.2. hot working, because of this friction, it is also characterized as, it is also called as a sticking, because the material starts to adhere to the surface of the rolls. The material starts to stick to the surface of the roll or the tool, that whatever tool we are using. That is why hot working is also termed as a sticking. Now based on this flow stress and maximum possible draft, we have the dimension of our workpiece. So the force, rolling force, would be equals to, that is flow stress into the area, and we have flow stress, average flow stress into the width into the length. So this is the force that is required to perform the rolling operation. So we have that approximated roll force can also be calculated using the width of the work and the contact length or between the rolls and the work. So consider the variation of pressure along the contact length. Obviously there is a pressure variation along the contact length, and that is maximum at the neutral point, as we have seen in the last slide of no slip point. So the contact pressure reaches maximum at a no slip point, then it further reduces. There is a entry point, we have the exit point, right? So the pressure reaches maximum at the no slip point, as you have seen in the last slide. So here F is the roll force, and W is the width of the work, being rolled, that can be in millimeter or inches, or it can be in inches. And we have length, again the length of the workpiece, oh sorry, the contact length. This is the right contact length between the roll and the workpiece, that is also in millimeter or inches. So based on this we can see here, based on this one we can say the force would be equals to PDL, right? We know the pressure is force per unit area, the stress is also force per unit area, so we can calculate based on the pressure as well, and from length 0 to maximum length L, right? And it would be maximum at this point, so this force would be maximum at this point. So the contact length would be, how to calculate the contact length? We have that is L equals to under root R T naught minus TF. This is the contact length, and the torque, assuming rolling force is centered on the workpiece, we are assuming that the rolling force is perfectly centered on the workpiece as it passes between the rolls, and the movement arm would be, what will be the movement arm? It would be half, obviously. If the rolling force is centered at the workpiece, so the movement arm would be half, right? So we have force into movement arm, that is F into L by 2, or we can write it as 0.5 into force into the length, right? That is a torque produced in the roll. So the power required to drive each roll as you know, the power is a product of the torque and the velocity, you can say. So we have the torque, that is 0.5 FL into 2 pi n, right? And because we are assuming this is a torque for a single roll, this is the torque for the single roll, and the power required for each roll. But as we know that even the simplest rolling mill consists of 2 rolls, so that torque would be doubled for the power required. So our power would be equals to 2 pi n FL. So this is the power required to drive the rolls, and in this case we have, this is the force, this is the contact length as we have seen before, this is the roll force, and this is the number of revolutions for the roll. So this is how we can calculate the power. So the unit of the power would be joules per second for this power. Okay, now we have true strain, we have the flow stress for this one, right? We have calculated the rolling force, we have find out the contact length and then the torque produced and the power required. So these are 6 parameters that are used to analyze the rolling operation, that the strain that is required to be produced and the consequent flow stress that is required to produce this amount of strain, then the rolling force that will be required to produce such and such a stress values, and the contact length based on the rolling radius of the roll and the thickness of the work part. Then the torque produced because of this contact length and the force exerted, and finally the power required. So this is the simple analysis for the rolling operation. Now the next slide is about the flatness control and the defect in the rolling operation. So there is a phenomena that occurs in the rolling operation. Let's suppose we are performing a flat rolling on a work part. This is our workpiece. This is our workpiece, and you're performing the flat rolling. So the force are being applied at these extreme edges, right? So because of the force at being applied at the extreme edges, this roll bends, right? So because and this roll bends, so what we get at the so because of the rolls, because of the force that is being applied at the edges of this roll, there's a case of the 3-point bending, right? We have the load here, we have the reactionary force here, and we have the another force being applied at this extreme edge. So because of this, the roll bends at a certain curvature. So the resultant product we get from this kind of roll is like this one. So a product that is thicker at the center while thinner at the edges. So to overcome this problem, we perform the crowning of the rolls. Crowning. Rolls are crowned, and what is the crowning? That they are made in such a way that the rolls are thicker at the center while they are thinner at the edges. So what happens when such rolls are used in the rolling operation, and when the products get into the gap and the force is being applied, again the roll bends, but due to the bending they become flat. So ultimately the product we get is flat from top and bottom. So this is how we can save the shape of the product due to the bending. We can crown the rolls to compensate the roll flexure, you can say, or the bending of the rolls, and ultimately getting this defect in our final product. Since the roll deflection is proportional to the force applied to the rolls, product flatness can also be improved by measure to reduce the roll force. So one way is to reduce this defect is by crowning. The other way is that because this defect arises not only from this 3-point bending but also due to the high roll forces, so we should find the way out while performing or while designing the rolling operation. We should focus the way out to reduce the roll force. And when we'll perform some numerical analysis or we'll look into some problems of the rolling operation, we will see how we can reduce the roll force while designing the rolling operation. So now moving towards the shape of the rolling operations, the shape of the rolling. As we have discussed, there are two types of roll: the flat rolling operation, the flat rolling, which we have discussed earlier, and the shape rolling. So in the case of the shape rolling, the work is deformed into a contoured cross section rather than flat. So we don't have a flat cross section, instead we have some contoured cross section, like some specific shape, and the I-beams and different kind of beams we use during the construction, so they are formed by the shape rolling. So the accomplish by passing work through rolls that have the reverse of the desired shape. Obviously if you want to get some shape on our workpiece, so we design the roll with the inverse or the reverse of that shape. The products that are produced from the shape rolling include the beams or different kind of channels that we use during the construction. Most common example, another common example for this one is the rail tracks and different profiles of the bars and rods. So we have the blooming rods, or we can have the edging rolls which thicken the work part from the edges. We have the roughing horizontal and vertical rolls. So we have two horizontal rolls and there are also vertical rolls to roughen the sides of the workpiece. We have the intermediate horizontal and vertical rolls, again the edging rolls to produce the sharp edges, and we have some other finishing rolls. So different kinds of rolling profile can be shaped based on the type of the product we want to achieve. Now moving towards type of mills. So mill is you can say a setup on which the rolling is performed. So it has two rolls that are designed to apply the pressure onto the workpiece, that is termed as a rolling mill. So it's a massive and expensive equipment. So we can have multiple configuration of the rolling mills. We can have the two high rolling mills, that is a most common one. We have the two large diameter rolls that are exerting the pressure onto the workpiece. We have the three high rolling mills. The two are exerting the pressure, and we have a platform here. So once the workpiece gets here, this platform transfer the workpiece on the upper platform, and then there's another pass on the third row. We can have the four high rolling mills in which there are two back rolls, and there are two back rolls that are exerting pressure onto the smaller rolls, right? So that can perform the rolling operation. The purpose of that is to reduce the roll force, because the diameter would be reduced, so we will have the lower roll force required. Then we have the cluster rolling mill, like we have multiple rolls that are used to make strips. So we have the large roll exerting on the smaller one, then the smaller one are exerting onto further a smaller one. Ultimately we have very small rolls that are exerting pressure, the force onto the strips, so they are used for the thin sheets. Then you have the tending rolling mills, as we have discussed earlier. We have a workpiece which have multiple rolls in a series, so that is termed as in which we reduce the thickness of the work part gradually, so that is termed as a tending rolling mill. So these are some configurations of the rolling mills, and this was some in this lecture we have discussed the different numerical analysis, perform the analysis of the rolling operation. We have seen the how to calculate the rolling force, the contact length between the roll and the work part, and power that is required to drive the rolls, the torque produced during the rolling operation, and the sticking and the frictional effects on the rolling operation. So in the next lecture we will be performing some numerical problems regarding the rolling operation.